The particles of the medium move parallel to the direction of the wave's propagation. Compression and rarefaction occur as the wave travels. Examples: sound waves travel through air, water, or solids. Seismic P-waves, primary waves generated by earthquakes. Compression waves in springs, when you compress and release a spring or slinky. Visual: if you push a slinky forward and backward along its length, the coils move back and forth in the same direction as the wave. Transverse waves: in these waves, the particles of the medium move perpendicular to the direction of wave propagation. These waves have crests, high points, and troughs, low points. Examples: light waves, an electromagnetic wave. Water waves, on the surface of water. Seismic S waves, secondary waves from earthquakes. Waves on a rope, when you shake one end of a rope up and down. Visual: if you shake a rope up and down, the wave moves horizontally, while the rope moves vertically. Combination of transverse and longitudinal wave motions, making them complex waves. This combination occurs because water particles move in circular or elliptical orbits as the wave passes through. Characteristics of water waves. Particle motion. At the surface, water particles move in circular paths, both up and down and side to side. Below the surface, the particle motion becomes more elliptical, with decreasing amplitude as depth increases. Energy transfer. The energy moves horizontally, but the water itself does not travel with the wave. Instead, the particles move in loops, returning to their original position. Surface waves. Water waves are primarily surface waves, where the disturbance occurs at the boundary between air and water. Examples of water waves. Ocean waves, generated by winds blowing across the water's surface. Polarization refers to the orientation of oscillations in a wave, specifically for transverse waves, such as light and other electromagnetic waves. It describes the direction in which the wave's electric field, or another vector quantity, oscillates as it propagates through space. Types of polarization. Linear polarization. The wave oscillates in a single direction, plane, perpendicular to its propagation. Example: light passing through a polarizing filter, like polarized sunglasses, allows only waves vibrating in one plane to pass through. Circular polarization. The electric field rotates in a circular manner as the wave moves forward. If the field rotates clockwise when looking in the direction the wave is moving, it's right circularly polarized. If counterclockwise, it's left circularly polarized. Electromagnetic waves are waves that consist of oscillating electric and magnetic fields perpendicular to each other, and both are perpendicular to the direction of wave propagation. Unlike mechanical waves, waves do. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects. They travel at the speed of light and carry energy away from their sources. How gravitational waves form. Gravitational waves are generated by massive, accelerating objects that create disturbances in spacetime. Some common events that produce detectable gravitational waves include merging black holes, neutron star collisions, supernova explosions, binary star systems, two stars orbiting each other. As these objects move, they stretch and compress spacetime, creating waves that spread outward from the source. Detection. Gravitational waves. Because gravitational waves cause only minuscule distortions in spacetime, they are difficult to detect. Specialized observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo detect them by measuring tiny changes in the distance between mirrors separated by several kilometers.